So any questions from last time? So we were talking about ADS black holes of various kinds, ADS CFT in general, etc., etc. So what we will, so today we will sort of start with this idea that entanglement is kind of an important ingredient in understanding the black hole interior. Okay, so people have believed it maybe for the last 10 years or so, maybe even a bit more, 10, 15 years. So, but its full ramifications are still becoming clear. I would say even in the last couple of years, some things have become more clear, and in the last 1 year, So it's quite an active, and we are not going to get to that, even though I'll briefly mention some aspects of it. So, overall, so that's the direction that we are going to sort of explore starting today. And
I have a question previously.
Sure.
So you mentioned that the small ADS black holes will not be important for dynamics.
Yeah, basically their free energy is always higher than that of the small black, or of the large black hole. Free energy is higher or smaller. I always forget the sign. So
Just can I think of it as that if the black hole is sufficiently large, then it does not get time to evaporate, and when it evaporates, and by the time it evaporates, it bounces and comes back, which does not happen for the small one.
yeah, I mean it's not a question of time so much as it's not So the time basically to the radiation to reflect back from the boundary of is the order of ADS length scale. So the evaporation times of black holes are much bigger. So it's not the time itself that is a point here. So the time is much smaller than all of these time scales. So that's thermalization, equilibrization in the sense of going to boundary and coming back is a much faster process. So, but the point is that, it's a small black hole doesn't take up as much phase space as as the radiation with the same amount of energy. So that's another way to say it. So for instance, yesterday I talked about thermal ADS versus ADS black, large and small ADS black hole. Essentially, the small black hole can evaporate, and that is less dominant, or it has less, it's the final radiation that is left in the system after the small black hole evaporates has more entropy, free energy, whatever, those kinds of quantities than, than the original system. So it can evaporate. So that's the idea. So there is more phase space in the radiation than in the black hole itself. But the black hole is very large. The point is that there is, it's a very high energy state in the CFT, first of all. That's the first observation or first consequence of Hawking-based transition. And then it is the system. The most high energy states in the CFT are naturally interpreted as black hole microstates. That's sort of the message. So to construct, so this raises some questions, for instance, if you want to construct a large ADS black hole from a system which did not have macroscopically a horizon is actually a slightly tricky question. Because most of the states that you have in the CFT as high energies are black hole microstates. So it would be, like if you just randomly picked some initial configuration, what you would call in most of the system, the collapsing black holes that we are familiar with in flat space, for instance, are much more similar to small black holes in ADS. So the large black hole is a somewhat exotic system. So even though we hope to learn, and there are some things which we hope to understand from it, etc., the large black hole is not something that one should directly compare with the black holes that we have in flat space. They are much more similar to small black holes, because essentially the small black hole is saying that the ADS length scale is not very relevant. That's what it is really saying. So the dominant phase in the system is just a thermal gas of gravitons at the end of evaporation. Okay? Yeah, so I think that sort of, there was a brief comment I wanted to make about small black hole evolution. So that kind of starts off that. So let me make the comment. I continue with the comment. So Let me just finish this since you asked this. So let me just finish one more statement, which is that it also gives you, from an ADS CFT perspective, an argument for why there are no, let's say, remnants. So we considered the possibility that if black holes evaporate, in principle, they could have this thing that mass decreases and decreases. So which means that you should have very light states in the system which have to have huge amounts of entropy. Right? That's what remnants, roughly speaking, are. So if you have a, the idea is that the macroscopic physics or the semi-classical physics seems reliable all the way till the black hole size becomes very small. So when the black hole size becomes small, the mass of the object is fairly small. But since entropy is, if you assume that the radiation is exactly thermal, there is no there is no information. The information has to be inside the remnant. So that means that there should be high entropy objects with very low energies in the CFT. So in other words, CFT states there should exist low energy states in the CFT with very high energy, very high entropy. So there should be, so such states just don't exist in holographic CFTs, in general CFTs in fact. Okay, so it's like another ADS CFT gives you one more reason via this small black hole evaporation sort of an argument that there are, and remnants are probably not there. Okay, so and small black holes are, as I said, much more similar to what we have in our universe. So I think it is reasonable to expect that those things will evaporate. Okay, yeah. So your question? Yeah.
So when you talk about holography,
yeah.
States mean metric.
So yeah, states doesn't necessarily have, states with semi-classical description, semi-classical bulk description usually contain metric, yeah. So asymptotically you expect everything to have some sort of an approximate metric-like description in terms of an empty ADS, but deep inside the bulk what happens is not that clear. So for instance, like if you could have highly stringy states in the bulk, or high, some debrane states or whatever. There could be all kinds of things which we don't have full description in semi-classical gravity. Semi-classical gravity is basically by definition a regime where space-time is roughly speaking smooth and all that kind of thing. Okay, so that need not be the case in full quantum gravitational states. So so the existence of the metric is essentially equivalent to the assumption that there is a semi-classical bulk description. So that happens only in some regimes, approximations, etc., etc. Any other question? Okay, so I wanted to start off by saying a couple of words. So this is again a simple picture, but it has gotten a lot of applications. It's a kind of a thought-provoking picture. So I mentioned when we talked about the Hartle-Hawking state that you have, this is the kind of expression that I wrote down for, this is our typical Thermofield double state. So this is what we call the Hartle-Hawking state, and this corresponds in some sense to the state of semi-classical, let's say, scalar fields living in the background of a black hole. Semi-classical states in the bulk, okay, for an eternal black hole. So the point is that this picture makes most sense for large black holes in ADS. Okay, so for large black holes in ADS, you expect them to be definitely, thermal states. You expect them to exist as stable states in the, let's say, microcanonical ensemble. Okay, so so the natural description. So there is a natural. So this picture that we always draw, in some sense, makes most sense for heavy states in the CFT. So somehow, if they can be approximated by thermal states, then this is the picture that one can draw as a way of understanding the purification of a heavy state which looks thermal in the CFT. Okay, so this is a purification. Note that what we have done here. So this is a picture that Israel basically within a few years of this thermal, all the thermal stuff of Hawking and Gibbons and all those people. So once it came out, this picture, that the idea that the Thermofield double can be used as a prescription for talking about the eternal black hole was suggested by Israel very soon after. It's a remarkable idea. So, but the only thing is that in flat space, as we know, black holes evaporate, so it's not completely clear what is the approximation or regime in which this sort of a statement holds for the black hole. But in ADS, for large ADS black holes, based on my discussion from last time, one can imagine that for a thermal state, a heavy thermal state is eternal, is truly eternal. So which means that you can basically write it in terms of this Thermofield double state like this and give it a natural interpretation in terms of one CFT living here and one CFT living here. Okay? You should not think of this as, this is not the same thing as the ADS cylinder. ADS cylinder has two sides, ADS2 especially has two sides. So two sides of the two ends of the cylinder. So this is basically standing for one whole ADS spacetime. And this is the place where the bifurcate horizon is. And then this is some other asymptotic region where there is another CFT. Okay, so there are two CFT, CFT1 and CFT2. Okay, so basically, so the prescription, and this is Israel, and after IISc, Maldacena suggested that, in a paper that has gotten a lot of attention, that this is to be interpreted really as a statement in the CFT. Okay, so this just literally you take it as a statement in the CFT. So and note that that directly follows from our statement about state operator correspondence as well as the extrapolate dictionary in IISc. So each of these states are basically eigenstates in some sense. Okay, so I mean, so you think of it as you are able to do in bulk effective field theory. So this is the claim in some senses that you are able to write this down in bulk effective field theory. So in bulk effective field theory, this is not very completely clear how to define it for arbitrary states with arbitrarily high energies, etc. But it's sort of like a prescription. And so note that we wrote this down explicitly only for scalar field theories living on a fixed radius background, fixed eternal black hole background. Okay, so that's what we did this for. But let's assume, or let's think, or let's imagine that this kind of a construction is basically a statement about all the bulk states that are possible, and you're supposed to sum over all the states, whatever they might be, maybe stringy states, everything in the bulk. And if you take that point of view, then via the extrapolate dictionary, this has a direct map into CFT states. Extrapolate dictionary is basically saying that interpret this literally in the CFT. This is what interpret it literally in CFT. Okay, so this is the proposal. So the idea is that we know that in the bulk side there are bulk fields exist, and bulk fields in the limit when you take them to the boundary, they basically give you the boundary operators which form the spectrum of the CFT. Okay, so and boundary operators are nothing but states because of the state operator correspondence. So this has a literal interpretation in the CFT, and if you take it literally to be true in the CFT as well, then that's your, that's basically the Thermofield double construction in the CFT. Okay, but note that the picture is sort of, so that in that sense, Israel's picture become much more concrete in terms of the two decoupled CFTs. Okay, so and that's one thing that IISc will constantly do, which is that things somehow seem to always fall into place in the setting of IISc. You know what I'm saying? That's another reason why it is almost certainly correct. So like this is, so but the important thing here is that, so what is remarkable about this prescription is that once you make this statement, note that these are two copies of the same CFT which are not, interacting with each other. They're just completely decoupled systems. But the point is that we are looking at a state which is entangled between the two Hilbert spaces. So there is a Hilbert space of CFT, a second copy of the same Hilbert space of CFT, and you're looking at a specific state in the tensor product Hilbert space of the two things, which is an entangled state. And that entanglement, if you take this picture sort of literally, then it suggests that entanglement is what is leading to the interior of the black hole. Okay, so if you just if the state was just if you had two copies of, let's say, two black hole microstates, you would basically have microstates probably have some structure at the horizon or whatever. Let's draw some caricature like this. So there will be two copies of the state. That's all you will have, and you don't have an interior. Okay, so the bulk side of the state, asymptotically it will look like ADS, okay, and asymptotically look like ADS, and near the horizon, some microstate, we don't know what happens, let's say, for an individual microstate, but something happens. But, so if you take two copies, then basically they just sit there. But the claim is that the Thermofield double, if you construct this for the entire spectrum of states in the CFT, the idea is that somehow there emerges a semi-classical description in the bulk, which has this interior structure. Okay, so how exactly one should think about this emergence of the interior has not been very clear until very recently, but I think now that we have some better understanding of why that happens in terms of operator algebras and so on. Okay, so but this is the sort of the naive. So this is what should have happened naively. If you take two copies of a state, what is a big deal, right? I mean, you take two copies of the state, they're just sitting separately. So if one of them has a bulk description, you just have two bulk descriptions of two theories. That's what you have. But instead, if you take this entangled state between the thing, the claim is that the bulk interpretation changes, and you get this interior in the black hole. Okay, so this is a non-trivial. So, and it happens without interactions, it happens because of entanglement. Okay, so yeah, so precisely what is, how to take this picture, sort of make it precise, is a question that is still, it's a work in progress in some sense. Yeah.
Why don't we accept this description?
Which description? Because if the prejudice is in some sense that black holes have an interior. So that if you do not, for an individual, we don't have access to individual microstates, right? We only have access to the black hole as a macroscopic object, which is presumably thermal and all that. So if you take this to be, if you take an entangled copy of CFT states of this form, as so the statement that you have a smooth interior is what is being realized through the statement that this via the statement that so I don't know what am I trying to say here. So yeah, what I'm trying to say is that the idea that if you could do this, you could just say that if you take an entangled pair of two CFTs, there is no interior, and then you're manifestly sacrificing the smoothness of the horizon. Right? We don't want to do that. So that's a prejudice. So in that sense, that's why this is not a, this is by no means is it like, it's by no means like a derivation. It's by no means a derivation, but at the same time, it's very plausible. So, and generally speaking, plausibility arguments are way more powerful in physics than one might imagine. You know what I'm saying? So that's why we want to, so the question in some sense is, what is the approximation under which this is true? Of course, literally if you take two copies of the CFT and they're entangled, the real way to think about them is you should just write some space-time description like this with some weight. It's a purely mathematical way of writing it. There is nothing more going on, right? If you just did that, this is what you would get. This is just a bulk rewriting or a reinterpretation of this entangled state. There is nothing else going on, right? I mean, this is just, because the claim is that ADS-CFT says that these two things are the same. So, but there exists some approximation under which this bulk interior or the smoothness of the horizon emerges. So the question in some sense will be, what is that approximation? So that is the kind of the better question than like, many people do take it sort of literally, oh, this is, this is literally, there is, this is just a copy of these things, so obviously there cannot be anything. You know what I'm saying? So that is, I don't think that's the right approach. So the right approach is somehow to identify what is the approximation under which this is true. So and I think that is the setting in which I think the recent progress in terms of this one-Neumann algebra is kind of interesting, because I think
The CFT does predict an interior for the, like at some point.
A predictor, yeah. I mean, if you want to take, the way in which it happens is we got a thermofield double state from the Hartle-Hawking bulk calculation, right? So that we got a thermofield double state in the bulk. Then we are taking ADS-CFT, the extrapolate dictionary of ADS-CFT, sort of literally and applies it to all states, so some sort of like a very literal reading of this. Very literal means it's not completely clear whether one should read it. It's not really a derivation because of that. Because the point is, this calculation was done with a fixed black hole background with some, the scalar field fluctuations are on it. And really we derived it only for the scalar field vacuum. But then we are kind of making the claim that this, instead of thinking of this as eigenstates of a scalar field living in a given black hole background, you think of it as every possible state in the gravitational description, which by ADS-CFT is the same thing as every state in the CFT. So we take that literally to be the case. Let's do that, and that's where the leap of faith or imagination or whatever comes in. And then at that moment, then you have this picture that, somehow the eternal black hole picture that we had here is really the same thing as an entangled state in the CFT. But we have the burden and probably an opportunity to understand the interior of the black hole. So that's the setting. Yeah, I don't know whether I answered your question completely convincingly, but I think it is not convincing to the extent that the black hole interior is still mysterious. You know what I'm saying? So let me leave it there. Any other question?
So entanglement is there, is the implicit assumption that smoothness must go into the...
So can you repeat?
So entanglement is there between the two structures.
Yeah.
Implicit assumption that smoothness must be there, and we should formulate our theory based on that.
Well, I mean, okay, on the bulk side, we essentially derived this by demanding smoothness of the horizon. That's how we derived it, right? So then we got this expression, and then via ADS CFT, we say that this is true in CFT as well. So then it becomes, like in CFT on the other hand, these are two decoupled systems. So how exactly does the interior form? Okay, so there is a so it's not, the statement is, okay, so there is, so this has been sort of generalized into this idea, what is called ER equals EPR. Okay, so this was an idea of, or at least a kind of speculative comment by Malstein and Susskind. So ER is basically, you know, it's like Einstein and Rosen. So Einstein and Rosen wrote a paper long ago where they considered the possibility that there are these, you know, these regions are basically wormholes, as we discussed, right? So any slice through it is a wormhole. So Einstein and Rosen were, but I think I've never actually looked at the paper, but I assume that paper basically is one of the first places where they actually talk about this interior, you know, the wormhole structure inside. So EPR is of course the famous paper where they used entanglement to argue something about, you know, the non-locality in, you know, quantum mechanical states and so on. So that's essentially entanglement. So the claim is that entangled states, at least of a certain kind, always correspond to wormholes. So that's what this ER equals EPR conjecture means. So Einstein and Podolsky and Rosen. Okay, so this is more like this is one more step further from where I am here. Where here I'm basically just, you know, this is essentially the only leap of faith here is that, you know, semi-classical bulk fluctuations, which is where I derived it. I'm kind of thinking of this as now the entire spectrum of the states in ADS quantum gravity, which is the same thing as a set of CFT states. So that, if you make that slight leap of faith, this whole thing, this statement is true. Here I'm making it even more further, even more somehow general. I mean, and it's much less well defined. It's more like a speculation, hope, etc., etc. You know what I'm saying? So the idea is that if you have certain class of states, again the question then would be what class of states is the real question. So what kind of entanglement is where you end up finding wormholes of some kind? Okay, so in some sense you could imagine that even the standard, you know, bell pairs, they have some wormholes connecting them or not, you know. So of course if because that's like if you are working with some weakly coupled spin-like system, then the wormhole is some highly quantum wormhole. So there is always this kind of like a trade-off in ADS safety, which is that when things are, you know, easier or better defined or better controlled in the CFT description, then the gravitational description is largely useless, and the vice versa. So then there is yeah, so depending on the parameters of the problem, it might go from one description might be better than the other. So, but this is the sort of the general philosophy. Okay? So I don't know whether I answered it, but I didn't fully understand your question. Is that okay?
Yeah.
Okay. So, yeah, so this is EPR equals ER. Any questions on this? I think this is all I will say about this. This is the sort of the general picture, and it, you know, it comes in handy for various things, and it has been used extensively. And we may have occasion to talk about it maybe in the future, whatever remaining future we have in this course. So, but other than that, so this is the main picture.
So isn't this a non-local description? If two entanglements are connected by a wormhole,
yeah.
Isn't it a non-local description?
What do you mean? What is wrong with non-locality? I mean, we know that quantum mechanical states are non-local in the sense of ER, right? Or EPR, right? So, yeah. So, for instance, so there is a question of, you know, wormholes have a notion of traversability. So, the wormholes here are not traversable. If you jump in from here, you will hit the singularity. You will never be able to get here. So, and that is sort of the equivalent. And that is one of the checks, let's say, within quotes, checks of this claim, that, you know, this is equivalent to the statement that you cannot transmit information using bell pairs, right? So there might be bell correlations which are space-like separated. That's the nature of the state. That depends on the state that you start with. But that doesn't mean that you can send information from here to there. So the person who's doing experiments at Andromeda does not really know anything about what is happening here, and they can only compare their results later when both their information have crossed somewhere in the future in the collective light cone. See what I'm saying? So it's not like, so the fact that, so non-locality is always there even in the vacuum states of quantum field theory. So that's essentially this sort of entanglement is always there, right? Ground states have this kind of entanglement. That's why Minkowski is basically the Thermofield double constructed from two Rindlers. So that's why, anytime there is no firewall in flat space, we have some form of entanglement. That's what we showed in one of the small calculations. So the reason why space-time looks smooth is because of this entanglement between the different tensor factors at each spatial, on a spatial slice. So that's the statement. So, but that doesn't mean anything particularly about, non-locality in the state it doesn't give you any, buyable money, so to speak. It's not like there's nothing in it. I mean, there's a lot in it, but it's not really it's not about information propagation. So, yeah. Any other question? Okay. So one more thing I will add about this is that there is a version of the information paradox that you can construct using this Thermofield double state, which is a little bit different from the information paradox of Hawking, which we sort of resolved in some ways. At least qualitatively we understand what might be the resolution. So, I mean, not completely, obviously. I mean, there's still the problem, I would say, is at the bulk level is still, at some level, it's definitely open. But I'm saying that, there is another version of the information paradox that you can construct, which is you start with this TFD state, and you compute two correlators, which are, some correlators, which are separated in time. Okay? So you can do a bulk calculation. I'm not going to do it, but it's not super hard. This is what happens. Okay, at very late times, if you compute the correlation function you can think of this O1 and O2 as boundary values of two scalar fields living in the bulk, and then using the scalar field in the bulk and the eternal black hole geometry, you can basically compute that by solving wave equations in the bulk and so on and so forth. Okay, it's a fairly straightforward calculation. And also there is another way to argue that this happens is essentially because if let's say that this O1 and O2 are on two sides of the eternal black hole. So that is maybe the setting in which I think originally this was suggested. Let's say you have some O1, so this is at t equal to 0. So this is at 0, and then there is some O2 which is at some time t, and this time is very late time. Okay, so at very late times, and note that this t is an arbitrarily long time interval. So it's all because of the Penrose diagram that it looks finite. So this time is very late, and essentially you can show. I mean, you can compute it more or less directly, but also you can show it using computing the geodesic between these two things. That's roughly what contributes to this calculation. Okay, so you can compute the length of the geodesic, and the length of the geodesic will basically scale as exponential of. The length will scale as t, so the correlator will scale as in this way. So I'm not going to do the calculation because it's kind of a distraction, but this is a fact. Okay. I'm not saying that it is time-like. I'm saying that it's some geodesic. It can be space-like. So there is some geodesic between them, and then you compute this length of this geodesic, and then you end up finding that this is of this kind. Okay. Yeah. Well, I mean, there can be somewhere, if there is no correlation between O1 and O2 at all, it will be identically 0. So let's assume that there is, let's say, you can take it to be O and O if you like. Doesn't matter. So there is some scalar field operator. The specific operator doesn't really matter. So you take some O, which is the dual of some scalar field in the bulk, and then you compute this OT, So this object, for instance, in the vacuum, we know what its form is. So there definitely has some correlation, right? It's a scalar field in the vacuum. But this is not the vacuum. This is in the Thermofield double. So, and the point is, in the bulk, so this statement is basically saying that this is the Thermofield double calculation that we are doing, okay? So, and then we compute this, okay? And then we find that it looks like it is basically, so essentially what we are saying is that if you compute, if you think of the Thermofield double in this, interpreted as a Thermofield, the thermal state interpreted as a Thermofield double, and we compute the 2-point function, at very late times, the correlator dies off exponentially. So which means that by going to arbitrarily late times, you can make it arbitrarily close to 0. So this is what one calls, the system is forgetting the initial conditions. That's what you mean by, that's another way in which people characterize this phenomenon. Okay, so because it means that by going to arbitrarily late times, you can make this arbitrarily small. So that's why it is, the system is forgetting the information. But if you had a pure state which was a stand-in for the thermal state, okay, in some system, okay, you can actually argue that at late times this will always go like this. Okay, very roughly speaking, this doesn't even require black holes or anything like that. This is a general statement about thermal state in complicated systems. The idea here is that thermal state this is very closely related to the fact that typical states are exponentially close to thermal states. If you have a general state in a complicated Hilbert space, that state will be exponentially close in entropy to the thermal state. So this is sort of like a version of that statement, and this is true for any, generally speaking, thermal systems. Okay, so if you compute it in a pure state, which is a stand-in for the thermal state, correlators will roughly of this form at late times. Essentially, the idea is that you had some non-trivial functional dependence at early times, and then this guy basically, it has some fluctuations, whatever, it hasn't completely forgotten it. That's what it means. It's a constant at late times. It doesn't completely die. So there will be, the fluctuations would have some kind of an amplitude or whatever, depending on where you draw this, that horizontal line. So there will be some fluctuations at the end, but this is not what happens if you have a smooth horizon. So essentially the idea is that things fall into the black hole and the exterior sort of forgets it. That's another way of thinking about it. Okay. So, and this version, so this is a version of the information paradox. It's a different version of the information paradox, and this is a version of the information paradox that is tailor-made for the eternal black hole in this language. And this is sometimes called the Malthus information paradox. Okay. So generally it is believed that this information paradox is happening because we are ignoring the full quantum corrections in gravity. So we are working with classical gravity, and we know that non-perturbative corrections in gravity, which means that other solutions can contribute which are not the black hole solution, for instance. So other non-perturbative solutions basically always go like this, or more in the context of gravity, non-perturbative corrections will always have this form. Note that G always comes with H cross in it. Okay, so remember that if you really want to think of this gravity path integral, it should be, there is a 1 by H cross, but then there is also the fact that there is a 1 by 8 pi G times d4x r and so on. Okay, so this means that G and H cross, in quantum gravity, G and H cross is always coming together. Okay, so this G contains H cross. So whenever I see non-perturbative in G, it should be understood that those are quantum gravity corrections. Okay, so this sort of corrections, because this is basically A by 4G is also S, right? So this is in some sense of the same order as S. So it's because we are forgetting non-perturbative corrections due to quantum gravity is why we are not able to reproduce this, and we are stuck with this, is the belief. Okay, so nobody has been able to really make it precise as far as I know, or at least maybe I've not been keeping track of it too much. But as far as I know, I don't think that a completely satisfactory answer to this probably is not known. But it's also like it is expected that this is the way it will resolve. Okay?
So,
yeah.
what do you mean by that?
System, it just means that exactly what I said, which is that if you wait arbitrarily long times, the correlator can be made arbitrarily close to zero.
Our system is the boundary system in this paradigm.
Yeah, you can think of it as boundary system or the via ADS CFT interpreted in the bulk in this way. So either way, but if you do a bulk calculation in the semi-classical geometry that I've drawn, you will find that this correlation function dies at late times exponentially. Okay, so and there are various ways to do it. I've not shown you how to derive either of these things, but the derivation is not very important. You know what I'm saying? You can do these things. It's not super easy either, but it's not also very hard. So this is a very general statement about any statistical mechanics system which has a thermal state. So this state is basically some microstate. It's important that this is a microstate, because if you truly have a pure state and not some lossy state, not some thermal state or something which doesn't have any loss in it, it's a unitary kind of thing, then this has to be, at late times it has to behave like this. And this is, on the other hand, here you see that at very, very late times it can get arbitrarily small, right? In particular, it can get smaller than this. So that's a form of information loss.
So, is it some kind of indication of chaos in the CFT set?
Well, I mean, it's not quite chaos yet. So this is more like thermalization. So this is more, they're related. So yeah, I mean, you could say that the fact that this is sitting there in a unitary theory is sort of, it's not necessarily the case that you have to, chaos is a more precise statement in the sense that there is a certain, speed or whatever, in which like correlators mix and so on and so forth. I'm not making any of those statements. I'm just saying that at very late times, this is what happens. Okay, so this is a bare bones requirement. So those are more sophisticated questions. This is just a bare bones requirement from the fact that your system is not losing information. So, and that already is lost by this bulk picture. Okay, any other questions?
So psi is a microstate in the CFT side.
Psi is a microstate in the CFT side. That's psi is a microstate in the CFT side, but by ADS-CFT we expect it to have a dual description as well. But the point is that here, because this is close to a thermal state, we are replacing it with a thermofield double. Okay, because this is some heavy state which looks thermal to us. So if you just blindly replace it with a thermofield double, what we are seeing is that there is information loss. And that's due to the smoothness of the horizon. And the end message is that this is not, if you want to really resolve the microscopic information in a state in the CFT, you cannot approximate it to some thermal state or its thermofield double replacement. That's really what the message is. So, but how do we incorporate that into the bulk calculation is the question. So, and so the general belief is that we are not keeping track of non-perturbative corrections. This is the general belief. Even though, as I said, I don't think it is a fully satisfactory resolution is known. Okay, so okay, so I think that's basically all I wanted to say about this, sort of the entangled black holes. So now I think we can switch gear and we want to talk a little bit about entanglement entropy and holographic entanglement, Ryu-Takagi and so on. Okay, so which hopefully will be, at least I don't think it's kind of straightforward and simple. So hopefully we'll be, if you have any questions, of course feel free to ask. So first I want to say, so we all know what entanglement entropy is. So let me start with entanglement entropy and then I'll slowly migrate to holographic entanglement entropy. Okay, so this part will be fairly fast because I'm assuming that you have all seen at least little bits of it and we don't need too much of its detailed workings anyway. So, okay, so this is, so if you have a system A and its complement B, A and B is, let's say, the complement. Okay, so then I'm defining it for a bipartite system at the moment, at least. Doesn't have to be, actually. So the density matrix is more generally defined. But let's imagine this situation where I'm also going to draw a picture, a suggestive picture, which now I think you should all be sort of comfortable with. Let's consider some subregion A on the boundary. Okay, and so this is, if you can just picture ADS3 CFT2, because CFT2 the boundary is on a cylinder. Okay, so the CFT2 on a cylinder, this is A, and this whole other rest of the circle is basically B. Okay, so this is something that we are familiar with in quantum field theory, which is that the Hilbert space is represented, is basically one way to think about the spatial slices are basically the Hilbert spaces of the theory. Okay, so if you do a bipartitioning of your Hilbert space by considering some subregion of the spatial slice, then A is a tensor factor and A complement, which is B, is also a tensor factor. Okay, so this is a very crude picture. In quantum field theory, as I said, it's not strictly true, but it's good enough for our purposes. We'll make some clarifications as we go. Okay. So the picture is, we have ADS D plus 1. So, and the boundary is S D minus 1 times R, where R is the time. Okay, and so you can keep ADS3 CFT2 in mind, which is easy because everything is three-dimensional. Okay, so the boundary is two-dimensional and so on. Okay, so So this is the this is what entanglement entropy is. Okay, so this is entanglement entropy of a subregion in the quantum field theory, the CFT. So this is a complicated object to compute. typically speaking, this quantity is difficult to calculate. In free quantum field theories, people have been able to make some progress and so on. But in interacting quantum field theories, which is what we are interested in, because as we know, when semi-classical bulk Einstein gravity holds, the dual theory is strongly interacting. Okay, so in the strongly interacting case, generally speaking, we don't know how to compute it, but people have managed to do it just using conformal symmetry and related arguments in 2D CFT. Okay, so what Ryu and Takagi said was that ADS CFT provides you a simple way of computing this quantity, despite the fact that the dual theory is complicated. So the dual CFT is a complicated theory, and we don't know, except in 2D CFT and to a lesser degree, 2D CFT is probably the most controlled setting in which we can actually do these calculations in the CFT. Okay, so I'll write down the formulas eventually, but at least we know some formulas there. But in general interacting CFTs, we don't know what they are, and it's hopeless, basically. So, but on the other hand, what Ryu and Takagi said is that, so they suggested a bulk mechanism, bulk technique for computing these entanglement entropies, for computing these subregion entanglement entropies, computing these subregions. So this A and B are what I'm calling subregions, okay, or boundary subregions, because they're subregions on the boundary of ADS. So subregion EE. So what they suggested, so look for codimension 2. Codimension 2 extremal area surfaces. I'll explain what all this means in a second. Let me just first write it. Area surfaces. Sigma in the bulk with okay. So we are interested in computing the entanglement entropy of the subregion A. So what they are suggesting is that you first look for extremal surfaces in the bulk which are anchored to the boundary of A. Extremal surface means, surfaces that minimize the area. Okay, if you compute a bulk area, a bulk surface with this anchor to the boundary, you will find that there exist surfaces which extremize that area or minimize that area. You can think of the minimal surface also, it's not very different. Okay, so d sigma equal to dA, and yeah, I mean if there are many of them, you take the minimal one. Okay, there are sometimes in multiple extremal surfaces, then you take the minimal one. Take minimal one. And there is also one more condition called the homology constraint, which I'll say in a second, but let me not get into that right now. Take minimal one if there are many. So Ryu and Takagi, basically what they said is that once you determine this extremal surface, the entanglement entropy of the entanglement entropy of A in the CFT. Okay, we are trying to compute a CFT quantity. Note that this is a CFT thing that we are trying to compute. These are entanglement entropies in the CFT. So the entanglement entropy of the CFT can be obtained from this minimal surface or the extremal surface that we computed and divided by 4G. So this is their prescription. Okay. So is that statement clear? So note that it is a conjecture, but we can explicitly check it in 2D CFT, for instance, and that was their biggest argument for taking it as face value.
How does the surface look like? What is it on?
It's basically some surface that goes into the bulk like this. So this is the radial direction. This is not in the, so this whole thing is lying on this plane. So that's why it's codimension 2. So note that, so we are always, so codimension 2, yeah, so in D plus 1, codimension 2 basically means D minus 1. Okay, so this surface, I think maybe it is easier to actually, if I keep it less general. So if it is ADS 3, so the codimension 1 basically will be just one dimensional. Okay, so this is basically just a geodesic in ADS, a spatial geodesic, in ADS. So space like geodesic in ADS. Okay, so but it has to start at the boundary and end at the boundary. So that's the statement. So if you compute the area of that thing, that in higher dimensions it'll always be codimension 2, but in ADS3 it's just a geodesic. And in ADS3 is where we know how to compute it, because we can compare it with CFT. We'll do that. Okay. So this is what this is the prescription. So is that picture clear? Any questions? So this is the Ryu-Takagi formula, if you like.
So, if area as a function of this sigma is the entropy, then for different ADS systems, like for different values of D, the dimension of entropy will change, right?
What D means? ADS D plus 1 D.
Right.
So area is a number, right? What do you mean it changes D? Area is basically some number. So you can just compute. It's a real number, right? You just compute the area. It's like physically, just literally the area. So the only point is that you want to compute that area which is minimal, the smallest one. That's the minimal surface. It's kind of like a soap bubble in flat space on a ring, except it is in ADS.
But when D minus 1 is 1,
Yeah.
it's a line, right?
Yeah, it is.
Area is basically length.
Yeah. So area is always in all the discussions, that whenever I'm talking about black holes, area is a codimension 2 quantity. Area is we can call it hyper area and so on and so forth, but let's not waste time. We are all grown people here, so we just call it area. Okay, and in fact, this is always one thing. If you don't remember anything else from this course, just remember that this is the easiest way to fix the Newton's constant dimensionality, because it's universally true. So in any other place, you have to worry about this, that, everything, So this is the easiest way to fix G Newton's dimensions. Okay, how many L Plancks are there in a G Newton? So that you can always figure out by knowing that it's in this many dimensions. It's basically 2 dimensions less than the thing. Okay, any other questions? Okay, so this is the statement. So yeah, so let's check it. Okay, so let's check it in the sense, I said that the CFT is a quantum field theory. We know the first thing we know about the CFT is that it is a quantum field theory. So in quantum field theories, there are some general expectations that we have. Okay, so yeah. So let's start with, so this is the sort of the Ryu-Takagi prescription, and what we want to do is we want to first write down, or at least motivate this result in CFTs, and then we want to compute it. In the ADS side of the calculation, I'll compute it. The CFT side of the calculation is also computable, and you can see it in various texts and so on, but the ADS calculation is somehow very simple, so I can do it here. Okay, so yeah, so the entanglement entropy, so let's start with the entanglement entropy in QFT in general. So I'll make some general comments and then specialize to CFTs. So the first observation is that if you have 2 systems, whenever I write, so typically whenever I have 2 Hilbert spaces, A, B stands for A union B. Okay, so that's what it always stands for. So, but the point here is that what I'm claiming here is that in QFT, this sort of a tensor factorization structure doesn't really exist. Even though we often make that approximation and do various calculations and so on, this is not really true. And it's related to the fact that there is an infinite entanglement. There are short distances divergence in QFT. So let's say that you took one slice of space-time, and or maybe you can look at some spatial slice in 2 dimensions. Okay, so this is your A and this is your B, and you want to compute the entanglement entropy of let's say a quantum field in this space where you bipartition the system into A and B. And this is a calculation first done by I forget who was it done. So Sorkin and his collaborators. Okay, Sorkin et al. So, but it kind of laid dormant for a long time, so this was done for the case of free field theory. Okay, Sorkin's goal, in fact, was actually to understand black hole entropy. So this is like I think 1970s or 80s or something, very old paper, but it's kind of a sort of an anticipation of the kind of things that eventually in holographic setting it becomes much more precise. Here he could not make it fully precise. Okay, so what you compute, so what he did was he computed the, you can, because it's a free theory, you can approximate it by, the mode expansions and, discretizing space-time and various other things like that. So then he computed the actual entanglement entropy by treating this as a discrete set of, discrete spin-like system, essentially. Okay, so you have a bunch of spins sitting here and then this sitting here, and then you computed the entanglement entropy by explicitly treating it as a factorizable Hilbert space. Okay, so this is, ultimately this is not true, but this is the approximation that people often make when they are trying to do free field theory calculations or field theory calculations in which you discretize space-time. Okay, so he computed this, and then the result that he found, and this is the, the S of A here, is basically proportional to area divided by epsilon. So let's say we are working in D-dimensional CFT, D-dimensional quantum field theory. Okay, QFT in D dimensions. Sorry?
Underlying space-time doesn't matter.
What do you mean by underlying space-time doesn't matter?
Minkowski, the QFT is living.
Yeah, this is Minkowski. You can think of it as Minkowski, yeah. So, yeah.
If they were in momentum space, then we could have written it as HAB equals H cross HP.
In tensor factorization in momentum space? So, what do you mean? Like, see the... So,
the Hilbert space in QFT is like the Hilbert space of every point in P. The tensor product, big tensor product.
See, there is, I mean, momentum space is a little bit tricky. So, I mean, so the point is that, like, there is no, this is a statement about locality ultimately, right? So the interactions are not local in momentum space anyway. Right, so we are not, our quantum field theories are local in space-time, but they are not local in momentum space, right? So for instance, if you write down, because of momentum conservation, for instance, in integrals, you will often find terms like A of k and A of minus k, for example. So this means that these are not at the same point in k, right? So they are not, locality is not a very useful information in the k space. So I don't know whether people have systematically studied the entanglement structure of a quantum field theory in momentum space, but it's certainly less interesting than in position space. Right? In position space, we are interested in locality, so then it is meaningful to talk about some subregion, then how it goes, etc., etc. Right? So, and because of that, that's the reason why we care about whether this sort of a picture holds. It doesn't quite hold, but it nonetheless has features similar to that.
My question was different. Defining the Hilbert space of QFT, we do it in terms of the momentum space, and here the regions A and B are in Minkowski space.
So I don't think that we define it in terms of momentum space. What we do is, if you really want to define a Hilbert space for a quantum field theory, you have to start with the operator algebra. And then say that you do something called a GNS construction in order to define the Hilbert space on which it acts. Okay? So the important point is that there is no notion of a Hilbert space that you can associate to some particular subregion of space-time in quantum field theory. That is the statement. So there is only one Hilbert space, which is the Hilbert space of the theory. That thing exists. Okay? But for any particular subregion of the QFT, there is no such notion. So that's sort of the point. So if you want to talk about any notion of locality or some notion of things living in some subregions, etc., etc., you have to work in the language of operators, not in the language of Hilbert spaces. But this is actually in standard quantum mechanics, 0 plus 1 dimensional quantum mechanics, let's say in spins or something. This is a choice. You could have done it either way. But in quantum field theory, it's not an option. The true locality lies in the operators and not in the states. So that's sort of the point. So that's essentially related to the fact that, as I said, states in quantum field theory are entangled. They are always entangled. So in particular, you cannot go to a basis where there exists some states here and some states here. That doesn't exist. So that's sort of the point. Okay. So so let's say that this is d-dimensional. Then if this is d-dimensional, your spatial slice is d minus 1 dimensional. And so the area, area basically means this thing here. Okay, I'm not really committing myself too much to a plane or anything here. So this will be d minus 2 dimensional. Okay, so this was the observation of Sorkin. Sorkin, what he did was he basically just computed the quantum field, entanglement entropy of a quantum field theory on a spatial slice with some subregion, and he found that the entanglement entropy goes not as volume but as area. So it's not an extensive quantity. Okay, so and this is interesting. The reason why this was a very interesting result and people should have appreciated it back then already is because this is precisely how black hole entropy scales. Black hole entropy is also not extensive in volume. It goes as one lower dimension, right? So this is one property. So that this is an observation that Sorkin sort of almost prophetically made long before everybody else got on board. And this is sort of the first observation about quantum field theory. And you can, in principle, you can actually do this order by order to higher orders. Entanglement entropy of quantum field theory can be computed order by order in this short distance epsilon. So by the way, I forgot to mention what epsilon is. Epsilon is the scale at which you're discretizing the system. Okay, so that's the short distance cutoff that you're putting. So which basically means that somehow the entanglement is only happening across this boundary. So that's what it really means, and there is some small thickening of this boundary that you're doing, which is what epsilon is. Okay? So so you can think of it as a system of springs where the size of the individual springs, length of the spring if you like, is basically epsilon. It's literally that calculation that he did. It's a bit of a mess, but it's a very straightforward calculation. Okay, so if you do that, you find that this is the way in which, this is the leading behavior of entanglement entropy. There are sub-leading behaviors, but this is the leading behavior, and this is what is interesting for our purposes in general. Okay, so any questions? Yeah. So actually, let me call this X and Y. This is X, and this is Y, and so this is the area corresponding to the boundary of X. Okay. So that's what he computed. And another important fact, and this is actually very important, is that in quantum field theory, this behavior is universal. Okay? So this divergence that you get is not dependent on the state in which you do the calculation. For instance, you could work with some excited state, like instead of the vacuum state. So the leading behavior will always go like this. Okay, so this is, So this is again a suggestion that it is not a property, entanglement is not a property of the state, but it's a property of the algebra in operator algebra in quantum field theory. So that's another thing. So it's independent of the state. Okay, so, yeah, so now let's specialize, actually, let me erase this. Now let's specialize to the case of CFT2, okay? In general, as I said, this calculation was done by Sorkin in free theories, okay? But it's generally believed that it is a property of all quantum field theories, because essentially it is coming from the fact that interactions are local. Okay, so that's why the entanglement is happening only across the boundary of that region. Okay, so we expect that even though it was done for free field theories, it's universally it is sort of true. Okay, so the one place where, so in general for an interacting or strongly interacting quantum field theory, this calculation is not doable. So we don't know how to do it most of the time. So, but in the case of 2D CFT, roughly I think around the time when ADS-CFT came along, I think it is not independently, and around that time, in that decade or maybe around that time, many people did this calculation. I'm just going to write the result, okay? So here the point is that you have so this is a 2D CFT, which means its spatial slice is some line. Okay, and I'm interested in, so some subregion basically means a segment, let's say of length LA, where this stands for some subregion A. Okay, and so if I want to compute the entanglement entropy of this system, so the claim, so this was I think done by Cardi, probably, I don't know who did it first, but let me just write down the general papers which are in the general vicinity. So Cardi, Calabrese. So you can look at some of these papers. They're not super inaccessible. But in many of these things, so the actual calculation of this, for instance, is done in many reviews on Ryu-Takagi type of stuff. So the claim is that if you want to compute the entanglement entropy of a conformal field theory, 2D conformal field theory, in some subregion, then this is the expression that you get, where C is a quantity called the central charge. Okay, so you should think about it as keeping a schematic count of the number of degrees of freedom, just like N did in our N = 4 superangles theory. Okay, SUNN. Okay, so N square, or more precisely, it's more like N square, if you like. Okay, so it's counting the number of degrees of freedom in the conformal field theory. For instance, for a boson, it's 1, or a single boson, this is 1. It's roughly speaking the degrees of freedom in the theory. Okay, so this is what the expression that he wrote down. So these guys wrote down. So this is an expression. So note that it's sort of a trivial version of this area law, because in area law, in 2 dimensions, you should basically get some kind of a constant behavior. But instead of a constant, you actually have a log behavior. That happens many times in calculations. Even in many calculations in field theory, etc., you will see that where you are. So if it is a power law where you should have got a constant behavior, you will often find a log behavior. So this is not inconsistent with what we are saying here. Okay, it is still marginally consistent with what we are saying here. So it's just that in 1 + 1 dimensions, the interactions don't have sort of space to spread out. They have to kind of, it's a line. You have to kind of wait in line to get to the thing. So that's the point. So this is our expression. Okay. So the main result, in some sense, of Ryu-Takagi in their paper was that they could reproduce this and similar formulas in thermal states and all that. So this is a calculation that was done in the vacuum. Okay, so this calculation was done in the vacuum state of the conformal field theory, but you can do it also in the thermal state, and similar calculations can be done in ADS as well. So what I'll do is I'll basically compute this. Yeah, we have time. So I'll just compute this quantity in ADS. Okay, so let's look at this as so this is my x = 0 line. Okay, so this is actually, let me just draw it here again. So this is x-axis, and this is, I'll take it to be LA by 2, and this will be again minus LA by 2, just to make it symmetric and convenient. Okay, and I think of, by ADS-CFT prescription, I should imagine that this direction is attached to some holographic Z direction. Okay, so we know that the metric corresponding to ADS3, which is dual to the CFT, is basically this. This is the Poincaré patch of ADS. I'm looking at a line instead of, I drew that picture initially for the cylinder and the boundary circle, but it doesn't have to be. In any ADS-CFT setting, you can basically, whatever the boundary is, we can put a conformal field theory there. In the dual, again, you can do the minimal surface prescription. Okay? So, and I'm interested in looking at some t = 0 slice, so which means this part of the metric is gone. Okay, so this is in the vacuum, so everything is time translation variance, everything is there. So this is so now the metric is this. Okay, so this is the metric that I am supposed to compute the minimal surface, or minimal, in this curve, minimal curve. Okay, so the idea is that I want to look for a curve which goes like this, anchored between the two boundary points, which has some area here. Right? And I want to compute the minimal surface like this. So the minimal area surface here is basically just the length. Right? And if you have a metric like this, we know that the length is nothing but integral of ds, which here, let's say it goes to some, let's say Z max. Okay? Note that Z = 0 is the boundary of ADS in this Poincaré coordinates. Fine? So this is I'm trying to, so this x is a coordinate on the boundary of ADS. I'm looking at a t = 0 slice. It's really, you should think of it as a, tx plane is lying here, and the ADS is going upward from here. Okay, but I'm looking at a t = 0 slice, so I can do everything on the board. There is nothing confusing here. So, and then I can compute this, and this is just basically, so there is a L ADS sitting outside, and then I have, let me write it as a dz integral. So I'll write it as z times z prime square plus 1. This is the guy that I have to minimize, and I have to minimize it from 0 to z max, whatever z max might be. We don't know. We will determine it by minimize. We want the minimal area guy, right? So So from that we will see. So we will actually, yeah, so in effect I'm going to answer that question by leaving it as an exercise, but we don't know yet. You're absolutely right. So essentially what we have to do here is we have to solve the Euler-Lagrange equations for this. Okay, so but it's easy, it's fairly straightforward. That is the exercise. So minimize this functional. Okay, so, and you will find, so the result would be, yeah, this is Z prime, dz by, am I right? Yeah, it's dz, yeah, so if I take a dz integral, I think it should be x prime, you're right, I think, dx by dz, yeah, I think so, x prime square. You're right. So x is the variable, but I think I wrote it wrong. No, I wrote it right actually. Okay. So x prime square plus 1. Okay. So so this is like sort of so you can write down the minimization equations, Euler-Lagrange, etc., and at the end you will find that the curve that you want to write down can be parameterized in this way. Okay, so this I'll also have to make some comments about the zero, because ADS is infinite in volume and size in some sense. So if you integrate all the way to 0, you will find a divergence. So what you will actually do is make this into some particular finite small value. Okay, and you will see that this naturally gets interpreted as the UV cutoff in the CFT according to the Scadi-Calabrese type formula. Okay, so the answer here is L. Okay, so and it basically is a curve that goes from here to here. So when lambda is 0, this is the point. So this corresponds to z equal to 0 and LA by 2, and this is minus 0 and minus LA by 2. And so you have to solve the Euler-Lagrange equations to get that solution. You know what I'm saying? And I've written it in a parametric form. You can actually make it like, if you don't want to write it in by introducing this parameter, you can call it x is equal to square root of, that kind of thing. LA square minus z square, but then you'll have to do it on both sides separately. Okay? So by the way, so one thing I forgot is that I have to put a factor of 2 here, because this integral is going from one side to here, so I have 2 sides. Okay, so similar thing applies here. If you want to not use a parameter and write it explicitly as a function of z and x, then you'll have to do it in 2 pieces. Okay, so I wrote it like that because I want to kind of cover the whole thing in one shot. Okay, so anyway, so now that we have that expression, so we also know in the process of doing it, we have also determined z max. Right, that just follows from when lambda is basically pi by 2. Right, so that also you get. Okay, so anyway, so once you have the solution, you can plug it into this and compute it. Okay, it just follows, and the result that you get is that so the length of minimal surface, minimal guy, is equal to 2L times log LA by this thing. Okay, so this is your formula. And so let me just repeat what we wrote last time. This wrote in the CFT side, which was C by 3 log LA by epsilon UV. Okay, so this is what we found. So the nice thing about this calculation is that so this part has come out exactly as it is. Okay, so which it need not have, because it essentially means that somehow the cutoff that we picked here is the same cutoff that Calacardi and Calabrese, or that formula, it has been chosen, because the UV cutoff is kind of an ad hoc quantity. So in principle, we should only be able to fix this quantity up to scalings of epsilon UV. So and every time you scale this epsilon UV, you will correct this expression by some constant. Right? If you scale epsilon UV by some, let's say some alpha times UV, it'll just change an overall constant. But that constant doesn't matter. Still there is invariant information that you can compare between both sides. Okay? And these two expressions will match if you have, C is equal to 3L by 2G. Okay? But this is precisely the ADS-CFT relation between the central charge and the ADS length and G Newton in ADS-3CFT2. So this was a formula, in fact it was known even before Maltaseina and ADS-CFT and all that. This is an old formula from Brown and Heno. So who arrived at this idea that ADS gravity has the symmetries of a CFT, 2D CFT. They had come up with it for other reasons, which are a whole different other story, which is also interesting, but it's a different story. So this formula was known long before ADS-CFT, and in ADS-CFT people can actually check it also. But the point anyway is that this bulk calculation of Ryu-Takagi basically reproduces the Cardy-Calabrese formula when you have this particular relation, which is precisely the ADS-CFT relation. Okay, so this is, in some sense, you could argue this to be a derivation, a holographic derivation of entanglement entropy in ADS-CFT. Any questions? So I'll say a few more things, and like it's only 12:11, so 10 minutes more I'll take, and then I think I can close this section. Any questions? Nothing, right? So the next things are very easy. So, but it's. So
the inside is empty ADS.
Yes, this is in the vacuum. So this is the calculation of Cardy-Calabrese that I'm comparing is entanglement entropy of some subregion in the vacuum state, because it's a density matrix, right? So you have to specify the state. So you can do the exactly similar calculation in thermal state also. Then you would replace this bulk ADS geometry that I wrote with the black hole geometry, and then you can compute it again, and you again find match. Okay, so so these are the things that Ryu and Takagi checked before they wrote their first paper. So we can make a few comments. The first is, so let's make a couple of observations about entanglement entropy. So there is one more observation that I would like to make, which is a property of entanglement entropy called strong subadditivity. Okay, there are many properties of additivity. Yeah. Okay. So this is a property of entanglement entropy when you have, let's say you have a Hilbert space which is HABC, or three subregions like A, B, and C, or three tensor factors A, B, and C, and the claim is that SABC okay, so this formula is known to be true for quantum mechanical systems. Okay, so this is called the strong subadditivity of von Neumann entropy, or entanglement entropy. So, so there is sometimes people slightly distinguish between entanglement entropy and von Neumann entropy. Entanglement entropy usually people refer to when they are computing the reduced density matrix in a pure state. Okay, so von Neumann entropy is slightly more general. So you could have started with an original state which was a mixed state, and then you could have done bipartitions and some stuff like that, or tensor factors, etc. So there is no so when you say entanglement entropy, but I will not distinguish it, I'll just use it kind of indiscriminately. Okay, so this is the statement. So this is the statement that we want, and this is now it is actually for let's do it for pure states. Okay, so this statement was originally proved by Lieb and Ruskay in the context of quantum mechanical systems. Note that all of these statements are difficult to even formulate precisely in quantum field theory because of these infinities that are there. So, but in quantum mechanical systems like spin systems, when there is factorizable Hilbert spaces. So when I write ABC, it's understood that there is an HA, HB, HC, and then there is a total Hilbert space HA tensor HB tensor HC. Or with something else if you like. So at least it's part of some bigger system. So this is the kind of inequality. So this was proved for quantum mechanical systems by Lieb and Ruskay, and it's a very complicated proof. Lieb is a mathematical physicist, and he has proved very difficult theorems throughout his life. You know what I'm saying? And there are, like if you look at the, so this theorem is, the proof is essentially impenetrable. It's elementary in some technical sense. I mean, if you want to spend like a, a summer vacation or I don't know, a week. I have never tried to really read it. It's to my own embarrassment, but it's like, but it is a complicated proof, and it looks fairly elementary in the sense that there is nothing too complicated going on, but at the same time, it is, it's a difficult proof. So if you want, you can look at it. But the point is that another thing that ADS-CFT does for it is that it makes, it's kind of a Promethean thing, right? You don't have to be Lieb in order to prove this thing when you believe in holography. So it kind of brings down this statement to a completely trivial statement in the context of ADS-CFT, and I'm going to do it in the most trivial setting. So if you just believe in holography, and if you believe holography in flat space, you don't even need ADS. ADS is, in my opinion, is slightly harder. So I'm going to do the most simple version of this proof in the context when you have a screen in flat space, okay, in 2+1 dimensions where things are very easy. Okay, so I'm going to consider a screen. In ADS also, it's roughly the similar idea, but I don't think this is as widely appreciated as it should be. That in flat space with screens is the most trivial proof of Lieben, this strong subadditivity. Okay, so this is, generally speaking, people say that, the strong subadditivity proof in ADS is easy, but it still requires drawing at least curves with some care. So here I will show you that it doesn't require anything other than triangle inequality. Okay, so let's look at the proof of this. So there is, you have some subregion A on the boundary, and then you have another subregion which is B, and another subregion which is C. Okay, so this is A, this is A, this is B, and this is C. Okay, so this is, in some sense, this proof is kind of like one could think of it as also a statement about the generality of holography, because it doesn't even require ADS-CFT. So this is my subregions. So let me just name some of these things in this way. So this is, so the boundaries of this are P, S, R, and Q. Okay. So what I want to show is basically the statement that SABC plus SB is less than or equal to SAB plus SBC. So this is the claim of strong subadditivity, right? This is what I want to show. But so what does that mean? So let's assume that the minimal surface prescription is true even in flat space. So there is RT surface in flat space. So which means that the minimal surface corresponding to the A subregion would be this curve PS, right? And the minimal surface corresponding to B would be SR, and this guy will be QC. Right? So, and the thing corresponding to SABC would be A, B, and C, so that will be just PQ. Right? So this is PQ, so let me write PQ here. So PQ, and SB is basically SR. So the entropy associated to B is the segment SR, right? Right? And then you have SAB, which is it's the same chalk? Okay, let's hide it. Yeah.
Why can't you just make it?
What do you mean 0?
Like just trace the perimeter.
What 0 means? I didn't
The
understand.
minimal surface, like can't you just trace instead of drawing a straight line?
So this, what do you mean? This is the minimal surface? So if you have a flat space thing, the minimal surface between P and S is not this, right? It is this. Yeah. And it's actually, you should have asked this question in ADS. In ADS, it's a bit more surprising. Here it is completely obvious, right? So here there is an arc and this is this thing. But in ADS, but it is actually, like you might have thought that the shortest path corresponding to two, boundary points is through the boundary itself. But it's not true even in ADS. And you can convince yourself. So, but anyway, so yeah, so PQ plus SR is, SAB is basically what? AB is, so we have PR, and this guy is, SBC is QS, right? And the claim, so now on the other hand, we can write a new point O here, and this is something that even I can prove. So this is, so PR plus QS. So let's start with PR plus QS. So PR plus QS is the same thing as PO plus OR, just because those are lines, plus SO plus OQ, which is the same thing as PO plus OQ, plus SO plus OR. You can see that I'm taking so much pleasure in writing this. It's PQ plus this trivial equation, but it is So, so that shows that PQ plus is this, and that is nothing but PQ is, what was it, SABC. So this was, what was it, SAB plus SBC is equal to this, and this equality is basically triangle inequality, right? We are basically just saying that PO plus OQ is greater than PQ, right? So, and then you get SAB plus SBC. Sorry, SABC plus SB. And that's that. So it's the most trivial illustration of the complicated theorem of Lieb and Roskay. And I think that, as I said, the fact that it is so trivial, I have not seen it emphasized. Even in ADS also, it is a little bit more complicated. You have to do these curves will be curved. So you have to kind of be a little bit more careful.
In the equality there is an equality also, but in triangle inequality there should not be an equality.
Well, I mean, if the points are all collapsing in some sense, they can, right? So if there is some degenerate limit of this, where it will be true. But it's, yeah, you're right that it is not very interesting. So I think that's basically the end of today's lecture. So I will define two things, which I will not, most likely I will not need it for much of my discussions. But I'll just, since we have come this far, I'll just define two things. One is called relative entropy, and well, I think I'll stop here, actually. It's not, it's a definition, and if I need it, I'll introduce it later. So, yeah, I think we can stop there.